Okay, and okay, stream is working. I think maybe you should get a start, huh?
Yeah.
Yeah.
So,
okay. Johnny,
we're not recording also on the cloud. If you want to do that,
I'll do that. Yes.
Yeah. Cool.
Just as redundancy.
Yeah. All right. So thank you, Kunal, for coming. So today we have Kunal speaking. He is a researcher at Apple. He got his PhD at UC Berkeley, and then he worked at Microsoft Research, and then Google Brain, and then eventually Apple. And he's very much present both in the theoretical computer science communities. He publishes at Stock and so on, but also in the machine learning community and publishing at ICML, NeurIPS, and so on. And his research interests, of which I'm sure he'll be able to tell us more now, sort of unite the fields of computer science, differential privacy, and machine learning. And today he's going to talk to us about some problems in differential privacy and optimization, I believe. So stage is yours. Yeah.
Thank you. It's a pleasure to be here. Thank you for inviting me. Yeah, so I guess I guess at Apple we work on a bunch of things, including sort of private federated learning, just sort of theory of differential privacy, as well as machine learning foundations. Today I want to tell you about some of the work we've been doing on, I guess, on this problem that that's known as stochastic convex optimization. This is Stoch. I guess we've been doing a bunch of work on this problem. This talk is primarily based on two works with some excellent collaborators, Vitaly Feldman, Tomer Koren, and Hilal Asi. I guess Vitaly is at Apple with me, Tomer is at Tel Aviv, and Hilal is at Stanford, and he was an intern with us, has been an intern with us more than once at Apple. Feel free to stop me if you have any questions, if anything is not clear. I guess I'll try to not go too much into technical details, but sort of give you a kind of high level, perhaps impressionistic view of the techniques. Yeah, okay. So let me start with defining the kind of questions we are looking at. Oops. Okay, good. So I'll be talking mostly about what's known as the stochastic convex optimization problem. So this is sort of an abstract question that I would say captures a large parts of what we do in machine learning. So in this setting, you have some data universe Z. So this could be, for example, let's say points in RD, and you're trying to find the mean of these points, or these could be examples of from some space, say images and label pairs. These are assumed to come from some unknown distribution D, and we'll call this the population. And we're trying to learn something about this distribution, some specific aspects of this distribution. And we'll kind of summarize our learnings using some parameter that we'll call theta. This theta will be restricted to belong to some convex subset of RD. So if, for example, you're trying to learn the mean of a Gaussian distribution in D dimensions, this theta would just be the mean. If you're trying to fit a linear or a logistic regression model or an SVM model, this theta would be the parameters of the classification model. And we are trying to find these parameters in a way which minimizes a certain loss function. So this would typically be your some kind of loss function for your task. In the case of Gaussian means, this is just say the square distance. In the case of classification, this could be some proxy loss, such as the logistic loss or some softmax loss in the more general multi-class case. Okay, so that's the general setup. Moreover, we are given access to this distribution through a bunch of samples. So you have Z1 through Zn, which will come from this distribution. These will be assumed to be IID samples from the distribution D. And this is all we have. So given this data set, I'm trying to learn good parameters for the distribution D. Good. So the stochastic convex optimization problem, and for an algorithm for this problem, is given this set S, and it's required to output some parameter theta hat, usually in this convex space K, so as to minimize the following quantity that we call the excess population risk. So what's the excess population risk? So the population risk is just the first quantity here. It's the expectation of the loss function when Z is sampled from the distribution uniformly at random. Right. So this first quantity is how much risk is theta hat incurring. The excess population risk is how much you incur relative to the least possible value of that risk. So this quantity on the right that I'm subtracting is just the minimizer of the same expectation over all theta and K. Right. Good. So I guess the goal of a stochastic convex optimization algorithm is to make this quantity, the excess population risk, as small as possible. And I guess, as you can probably guess, the reason there is an excess here is that this is a statistical problem. I don't actually have access to D. I only have sample access to D. What one hope is that as the number of samples I have increases, this excess population risk decreases. In fact, goes to 0 as n goes to infinity. And we are typically interested in kind of the rate at which that's happening. Right? So this is a very, very well understood problem. It's been tons of work in the last couple of decades. And actually, before I can get to the rates, I guess I need to put some restrictions on these objects so as to, which you can think of just sort of normalization conditions. So we'll be looking today mostly at what's known as the L2 case, which basically means that the convex set K is assumed to have L2 diameter 1. So I guess more importantly, I'm measuring the size of K in terms of its L2 diameter. So for this talk, K will be the unit ball in L2 in the dimensions. And typically, to be able to say anything about this problem, we need some control on L. And it turns out the right way to control L is to control the gradients of the loss function. So we'll be assuming that the L2 norm of the gradient at gradient with respect to theta for any Z in this data universe is bounded by 1. Okay, so with this setup, this is more or less fully understood. Turns out that the optimal excess risk that you can achieve for this question varies goes down to 0 as 1 over square root of n. So if you give me n data points, I can make this quantity roughly 1 over root n. I guess with high probability or an expectation, all kinds of statements can be made. And in fact, we know that you cannot do any better than that. So there's some sort of just the fact that I only have statistical access to D prevents me from going below 1 over root n. And I guess you can think of this 1 over root n as coming from the fact that if I gave you n outputs from a coin, and your goal was to figure out the bias of the coin, you can only figure out the bias up to an additional additive 1 over root n. So that's roughly intuitively this 1 over root n. Good. Okay, so that's the stochastic convex optimization problem. Today we are interested in a differentially private version of this question. So exactly the same setup, except now the algorithm is also restricted to satisfy differential privacy. And I guess for this talk, I will be thinking of epsilon delta differential privacy. You can prove analogous results for other flavors of differential privacy that I will not get into today. Good. I will actually not be defining differential privacy. Given that I was assuming most people know what it is. So let me just say a few words about differential privacy. So I guess essentially the definition of differential privacy says that if you were to change one of the n examples from this data set, and let's say adversarially replace it by a different example, the change in the output distribution is controlled, and roughly epsilon measures some kind of an L infinity divergence between the two distributions, sort of multiplicatively how close are the two distributions. Delta allows for a small failure probability in controlling this odds ratio. Good. Okay, I guess I probably don't need to motivate why we want to train differentially private machine learning models, but I'll say it anyway. I guess we know that when you train machine learning models, they can contain information about the training data, and this may be undesirable in many settings, especially if the data contains sensitive information. So I guess kind of a very nice example of this is this recent work from Carlini et al., where they showed that I guess even a relatively small ML model, language model, GPT-2, when trained on a large corpus from the web, is able to not just memorize long strings, but also output them on queue. So I guess here they showed that if you start with this prefix written above and ask GPT to complete it, it basically outputs the precise contact details of some Peter W. And this Peter W is not somebody that is ubiquitous over the web. This is an example that occurs only a small number of times in Google search and probably even fewer times in the training corpus. So these models carry the risk of revealing a lot about the training data, and this is something which we would like to avoid. And differential privacy gives you a provable assurance that such memorization will not occur, at least for examples that occur a small number of times in the data set. Good. Okay, so with that motivation, let's think about solving the private SCO problem. Let me actually talk a little bit about a very related problem that you may have seen, which I'll call which is, I guess, called the private empirical risk minimization problem. So in this question, there is no distribution. I have S, and S is all there is. The goal is to just minimize the risk over S. So now instead of Z being sampled from the distribution, Z is sampled from the S. I gave you endpoints, find the best data for these endpoints. Okay. Now, of course, without privacy, this is just a convex optimization problem, and this we can solve exactly. There is zero excess empirical risk. But with privacy, you need to pay some penalty. This problem has a long history in differential privacy literature, starting with Chaudhry and Monteleone back in, I guess, almost 12, 13 years ago. And by now, we fully understand this, at least the L2L2 case of this problem. And it turns out the optimal excess privacy risk, so how much this gap has to be for any differentially private algorithm, it still goes to 0 with n, but the rate at which it goes to 0 is square root d over epsilon n. Okay, so a few things to say about this. First, for this talk, I'll just think of epsilon as being a constant, so don't worry too much about the epsilon. The nice thing is that it's going to 0 very fast. It's going as 1 over n rather than the 1 over root n that we had earlier. But there is in this numerator a square root d factor. So whereas for the SCO problem, there was no dependence on dimension. Now we have to have a dependence on dimension that looks like square root of d. Good. Okay, so now back to private stochastic convex optimization. As we said, any stochastic convex optimization has to pay 1 over root n, and therefore any private one will have to as well. So I have a 1 over square root n lower bound on the rate. In addition, it's not hard to show that the lower bounds for private ERM actually carry over to private SCO. And we cannot do better than square root d over epsilon n. So there are these two lower bounds, which are, I guess, incomparable in general, that hold for private SCO. And I guess one could wonder are these the only obstructions, or are there sort of other additional lower bounds that show up when we are trying to solve private SCO? It turns out that there aren't, and in fact, in joint work with Raif Basili, Vitaly Feldman, and Abhijit Thakurta, we showed that indeed the larger of these two lower bounds is actually an upper bound. So there is an efficient algorithm which gives you excess risk that behaves as the larger of these two quantities. So let's look at this a little bit more. In the setting that epsilon is constant, and let's say d is about n. In that case, both of these bounds are like 1 over square root of n. Right? So what that's saying is that privacy is essentially free. I didn't pay any cost for, I didn't pay any price for ensuring differential privacy. I'm doing as well as I would have done just under the statistical constraint. Right? And what I'll talk about today, which is what we showed in this work with Ali Feldman and Tomer Koren, is that not only is this bound achievable, it's actually achievable in linear time. So there's no computational overhead either. So yeah, so both in terms of the runtime of the algorithm, as well as the excess risk, under the assumption that d is at most n, privacy is really free for this question. Again, up to constants. But, cool. Any questions so far?
There doesn't seem to be any.
Sure. All right. Cool. Okay, so to be able to prove such a bound, let's see what we need to do. I guess at the very least, we need to be able to prove what's known as a generalization bound. We need to say that whatever my algorithm has done is in the process of learning for the given the sample S it extends to this distribution D that I haven't seen. So this is what's known as kind of, yeah. So there are a large number of techniques that exist in literature on how to prove such generalization bounds. I guess the simplest one is what's known as uniform convergence, which says that sometimes my space is, my loss function and my space are such that with high probability, the loss over the sample will be close to the loss over the distribution uniformly over all theta. Unfortunately, when you try to use uniform convergence, the uniform convergence bound, or the best bound you can prove on the closeness between these two quantities, when you look over all theta, it's about square root d over square root of n. So doing this approach, you will pay this large overhead of square root d over square root n, which I guess is essentially 1 when d is n. So this technique doesn't quite work. There are other techniques. There's something called online to batch conversion, which says that essentially if you have regret bounds that hold for a single pass algorithm, then they will generalize to the population. Unfortunately, the best known ERM algorithms make multiple passes over the data set, and we will not be able to use online to batch for that. Another approach is what's known as uniform stability, which basically says that if your optimized, which is actually talks about the property of the algorithm itself. It says that if your optimization algorithm satisfies the property that for two neighboring data sets S and S prime that differ in one example, theta S is actually close to theta S prime. So this is roughly saying that kind of in a geometric way, theta does not depend too much on any one single example. Then you can prove some kind of generalization bound for the algorithm. These unfortunately also do not give us anything better than square root d over square root n. And finally, we can view differential privacy itself as a form of stability. And you can show that if your algorithm is epsilon differentially private, the excess loss is at most epsilon. The excess generalization loss is at most epsilon. And this can give you something slightly better than the square root d over square root n, but it will still, this approach will still not give you the correct answer. Right? So we need something different, something, so I guess what all of this says is that just using any of the existing ERM algorithms, we do not have ways to prove that those algorithms will extend to the population. So what we're going to do is we'll have to dig a bit into the algorithm itself. And the simplest algorithm that achieves the SCO bound is perhaps stochastic gradient descent. So this algorithm is one that I'm sure you all that we all know and love. So yeah, this algorithm basically starts at some theta naught and over t steps computes the gradient at some example, takes a small step eta t times gt in the direction opposite to the gradient, project back to the convex set and repeat. Right? And you output the final iterate. I guess I'll be using t for the number of iterations in this algorithm, which in general may be different from n, as we shall see. Where n is the number of examples I have, I may look at each example more than once, for example. Good, and I guess more generally, GT would be some kind of gradient estimate at theta t. And as written, it's at the tth point ZT, but I can use something more general, as we shall see. Good, okay, so this algorithm is of course not differentially private. It does give us the right 1 over root n rate, but if I want to make it differentially private, I need to add some noise, and turns out the simplest way to make it private is to noise up the gradient at each step by adding, say, Gaussian noise with variance sigma squared. So it's not hard to show that this algorithm is now differentially private. And if you follow through the analysis of sort of online convex optimization bounds, you can show that that when eta t is roughly 1 over square root t, the excess loss is something like sigma root d over root t. So I guess if I think of sigma to be 1, which is kind of the typical case to ensure privacy, I'm paying this large square root d overhead to ensure privacy. Right? Good, and I guess you could, yeah, so you could overcome this overhead with a larger runtime, as we shall see. So I can, for example, use batching. So I can, so the reason I had to add noise, which is scaled to constant times some privacy parameter, is that I'm computing the gradient, and one example can influence the gradient by an amount equal to 1. I guess each gradient has norm 1. But batching actually reduces sensitivity. So if instead of computing the gradient at 1 point, I computed the average gradient over b points, then the influence of any one example on this gradient estimate is now 1 over b. So I can add noise, which is essentially 1 over b times smaller. At each step, I'm still using an unbiased estimate of the gradient, so all the analysis still goes through. And if I ran this algorithm, let's say with the batch size being square root of t, which lets me set sigma to be 1 over square root d, I'll kill the square root d factor up here and essentially get rate 1 over square root t. Right, so this is good. I'm getting the right sort of 1 over root t rates after doing t steps. However, I'm now consuming square root d examples for each step, right? So each example, each step now uses not 1, but square root d examples. So my t, if I wanted to do 1 pass, my t can only be n over square root d, so I lose there. Or I'll pay in runtime. I could do multiple passes, and then I'll end up with runtime which is significantly larger than n. So this approach, it seems, cannot give us a linear time algorithm with the right rate. Okay, so this is what we will now try to address. Sorry, these slides are a little bit out of order, sorry. Okay, so I'll tell you about sort of, actually not 1, but 2 algorithms that achieve the optimal rate. And I guess they both have their advantages, which is why I'm talking about both of them. The first one is what we call Snowball SGD. And let me talk about that next. That's actually very close to the SGD algorithm that we were just exploring. Okay, so let's go back to that one for a moment, right? So here's our noisy SGD again. In our current privacy analysis, we said, look, my influence on this gradient estimate is bounded by 1 over b. And we add noise, which is scaled to 1 over b. That gives me privacy. I can just publish GT and go from there. That's essentially my privacy analysis, right? So this is good, but perhaps this is too conservative. Maybe I can take advantage of the fact So if I think of an example that's in the first batch, I computed the gradient, added some noise, and got to theta1, which is sort of the which is the parameter after the first step. But then I'm not really outputting theta1. I'm then taking another gradient step, and then more importantly, adding some more noise at the second step, and so on, and more at the third step, and so on. So I'm not necessarily outputting theta t. I'm only outputting theta t. I'm not even outputting theta1. So one would hope that the fact that I'm adding noise so many times, going from step 1 to step t, will give additional privacy to an example in the first batch. Right? Now, this isn't quite true in general, because the gradient in the second step is being computed at theta1, which depends on the example in the first batch. So if my loss functions were completely, could be very unsmooth, then this kind of an argument doesn't work. But it turns out such an argument does work if you make relatively mild smoothness assumptions. So in a work with Vitaly Feldman, Ilya Mironov, and Abradit Thakurta back in 2018, we showed that indeed an example in some batch PT gets privacy not just from the noise that was added to the gradient in that step, but also gets privacy from the noise added in subsequent iterations. So I can pretend as if all the noise added after this step was actually added to this gradient, and use that to argue about privacy. If you follow through this argument, it gives you kind of a non-uniform privacy guarantee. So the first example, or an example in the first batch, gets very good privacy guarantee because I added noise t times. But for somebody in the last batch, there's no improvement in privacy, right? They only get the benefit of one noise. So this also seems like a dead end. But here's a way to combine kind of the two ideas we saw and get an improved result. So we saw two ideas. We saw two ways of kind of reducing the noise, right? The first idea we said was to use batching. That helps reduce the noise, but that's costing me in sample complexity runtime. The other idea is to use this privacy simplification by iteration, which helps reduce the noise as far as the first example is concerned, but not really for anyone in the last batch. Right? So Snowball SGD basically combines these two ideas. It says, look, somebody in the last batch will only see the benefit of one noise. So let's make this last batch large enough. Let's make it size square root of t. But the previous batch will see two noises added, and I can make the batch size slightly smaller, square root d over 2. And as I go back from the last step, I can make my batches smaller and smaller. And I guess in general, I can make my batch size square root of d over s. And I guess this turns out to be the right thing because with this batch size, the sensitivity of an example that occurs in the sth last batch is about 1 over the batch size, which is square root of s over d. And the noise that this batch sees, so this batch is the sth last batch, so it will see s different Gaussian noises. So the total, effectively, that's equivalent to seeing square root s times larger noise. So noise is now also square root of s over d, if I set sigma to be 1 over square root d. Right, so I have now, by using this non-uniform batching, ensured that noise is scaled to the sensitivity for every individual example. while adding sigma to be like 1 over square root d, which is essentially the right amount to get the 1 over square root t rate, right? So I guess now the only question that remains is how many examples does this process consume in t steps? And if you just do the math, it turns out it's actually not very much. So basically the batch sizes are falling very quickly as you move backwards. And you can show that the total number of examples you use is essentially d plus t. So if you think of d as being n over 2, you can set t equals n. Which basically means that my n is now, my t is now n. Essentially, I'm getting the 1 over square root n rate. In one pass, oops, sorry. Yeah, so I guess this gives me the right rate because t is equal to n, and it's a one pass algorithm. Because it's one pass, it also generalizes, and I get the result I get. Well, almost I've lied a little bit. I guess the online convex optimization results hold for the average iterate rather than the last iterate. So this is not quite true. I cannot quite apply privacy amplification if I did the averaging. But luckily for us, there's been some progress on proving similar bounds for the last iterate of SGD, and we need to use those. So I guess it's a little bit more complicated than I suggested, but essentially the same idea does work and gives us the right answer. Good. I guess I'll also say that in practice, I mean, we designed this algorithm mostly for proving this result, but in practice, we've implemented it, and it actually is, even without any tuning, it's a very competitive algorithm. And it's not the best. There are like a well-tuned noisy SGD does work better, but this, even without tuning, is actually quite, that works quite well. Good. So that's all I'm going to say about this algorithm. Let me say a little bit about the second approach that we call iterative localization. So as I said earlier, I guess we were assuming that this convex set K has diameter 1. If you look at a little bit more closely at SGD, the one, instead of this diameter, we can actually think of the gap, the L2 distance between the starting point and theta star. So the excess loss as well as the sensitivity of SGD is roughly this gap over square root t. Right? Now, so what that means is if I run SGD over t steps, where let's say t is a little bit more than the dimension, say large constant times the dimension, then what I have done is I have localized the optimum a little bit. I have gotten to a point where theta star minus theta, I've gotten to a point which is not quite theta star, but is pretty close to theta star. And because I'm assuming that dimension is smaller than t, I can add some noise, and I would still be within, I guess once I add noise, the gap will be like square root d times this, this sensitivity value, which is not great. I'm not super close to the optimum, but I have at least reduced the distance from the optimum to, let's say, a half from 1, right? Because if this theta star minus theta naught was 1, d is t over 4, let's say. So this times square root d is half instead of 1. So I've made progress. I have reduced the diameter of the set where I need to look by a factor of 2. And now I can do this again. I can iteratively localize the optimum. And every time I do this, my my distance from the optimum falls by a factor of 2. And if I do this for about log d phases, I can get rid of the square root d overhead that I was paying and get close enough to the optimum. And I guess this approach is not, I guess the nice thing about this approach is that it's not restricted to SGD. You can use any stable ERM algorithm instead of SGD, add noise to get privacy. And this gives us a kind of more black box algorithm, which is more general. And I guess I'll probably not have time to say much about this, but the approach actually then, this iterative localization turns out to be useful in other geometries as well, not just in the L2 case. So, so it allows us to do more. I guess our work, yeah, as often happens in convex optimization, whatever results you get for the convex case, you can get the square of that for the strongly convex case. So, and that continues to happen with this case, requires some more work. I guess all of this does assume smoothness, which basically says that the loss gradient doesn't change too much between neighboring points, or equivalently, the Hessian has bounded spectral norm. We can actually extend these techniques to the non-smooth case, and the optimal rate is still the same. Unfortunately, we don't quite have a linear time algorithm for the non-smooth case yet. And I guess in this work, we presented an algorithm which gets you to n squared runtime. I guess we can improve it a little bit. And I think the current best results are somewhere between our n to a certain power, which is smaller than half, smaller than 3 halves, but we are still not quite at linear time yet. So I think that's one question that hopefully someone can make progress on. Okay, so let me then say a little bit about some other geometries. I guess mostly I'll be talking about this, what's known as the LASSO setting, or the L1 L infinity case, where I'm optimizing over an L1 ball rather than the L0 ball, rather than the L2 ball. And it turns out if you're optimizing over the L1 ball, you only need to assume gradients being bounded in L infinity. And I guess this problem has also been studied. So I guess a while back with Abhijit Thakurta and Li Zhang, we showed that the ERM question has excess privacy cost, which is roughly log d over epsilon n to the 2/3. And I guess as in the case of the L2 case, just the SCO part, you pay like square root log d over n. And I guess once again, you can ask the same question: is the larger of these two achievable? And in fact, what we showed in this paper that was at ICML last week, that in the smooth case, you can actually achieve the sum of those two lower bounds. And it turns out we need some new techniques to do that. This algorithm is actually also linear time, so that's kind of nice. If you don't make the strong smoothness assumptions that we need for this work, you do need to pay a price for dimension. So there is a square root d over epsilon n term that shows up. And we can actually, so I guess, yeah, so this bound is also tight. We can prove a lower bound as well as achieve this using the iterative localization technique I mentioned earlier with a very specific error descent algorithm as a subroutine. Okay, so Let me say a little bit about sort of this variance reduction technique, because I think it's nice and perhaps more broadly useful. Good. Okay, so recall in SGD, the reason we needed to add this noise was that I'm trying to hide this gradient, which is computed on one example. So I needed to add noise proportional to the gradient now. Right? So variance reduction is this general technique in convex optimization, which says, look, I can write my gradient at a point theta as in this sort of, I can decompose it in kind of a trivial way. I can write it as the gradient at a different point theta anchor plus the difference in the gradient between theta and theta anchor. Right, so far I've not done anything, but now if I replace each of these if I replace each of these two terms by some unbiased estimators for them, then I've made progress. So in particular, if you have a good estimate of the gradient at theta anchor and another independent, potentially independent estimate of the difference of gradients between theta and theta anchor, you still get an unbiased estimator. But the nice thing is that if your loss is smooth, then the second term, the difference of gradients between theta t and theta anchor, is bounded by the distance between those 2 points. So as a kind of dumb example, if my anchor point was just the previous theta, then because I'm taking these small steps, theta t minus 1 is only about eta. And so I've reduced the sensitivity to zt, if I use zt only on this right-hand side, by a factor of eta, which is like 1 over square root t. So I've significantly reduced the noise I needed to add to ensure privacy, if I only worried about privacy of zt. And if somebody gave me a good estimate of the gradient at this previous step. Right? This, of course, doesn't quite work because I need to handle the anchor point being reused, that the g hat at theta anchor itself will have to be computed on some data that may be reused multiple times, and I need to account for the privacy cost of that. And I guess it turns out there is a nice way to do it using some of the ideas we saw earlier. So I guess, as we said in the first third of the talk, one way to reduce sensitivity is to use batching. Right? So if I'm concerned that some estimate is being used, is incurring a large privacy cost, I can compute that estimate based on a larger batch to kind of make up for that, to reduce the sensitivity. And I guess doing this at one level doesn't quite work, but if you kind of build a full binary tree where the leaves are your time steps and each internal node corresponds to a point used, a batch used to estimate the gradient. It turns out if you do it the right way, you can actually get very good gradient estimates, which are not too sensitive to any single point. I guess I will just say that in the L1 case, the right algorithm to use to get the SEO bound turns out to be what's known as the Frank-Wolfe algorithm. And I guess the nice thing about Frank-Wolfe is that, so I guess we need an algorithm that allows us to get around this dimension dependent term that we would get if we were to add Gaussian noise. And Frank-Wolfe allows us to do exactly that. So at a high level, Frank-Wolfe says that if you average some linear optimizers for different optimization functions chosen carefully, the average of t linear optimizers gives error, which is about 1 over t. The reason we like linear optimizers is that if you're optimizing over the L1 ball, any linear optimization problem will have its optimum that lies at a vertex. So instead of computing this t-dimensional object, which is a gradient, and doing something with it, I just need to compute one vertex of this of the L1 ball. And it turns out that's a much easier problem. I can use the exponential mechanism to select the best vertex out of just these 2D. And the overhead of doing that is only logarithmic in the dimension instead of the square root t term that's unavoidable when I do noise addition. Good. Okay, so I guess I will not go into too many details. This doesn't quite work on its own, but this combined with some variance reduced version of Frank-Wolfe, I guess previously used in Sever et al. Allows us to get the right rate. And I guess I will refer you to the paper for more details on this. Okay, so let me basically stop here. So to summarize, we got the right rates for the L2 case as well as the L1 L infinity case. In both cases, for smooth losses, we can get linear time algorithms. In the non-smooth case, we can still get the optimal rate, not yet in linear time. And there's been some follow-up work on this recently. And in the process, we introduced some new techniques, iterative localization, this idea of using non-uniform batch sizes, as well as dyadic variance reduction, which I think will be more broadly useful. Yeah, so I'll stop here and take any more questions.
Great, thank you so much. That was a great talk. We don't have any questions from YouTube, so I'm going to stop